Welcome to the Foundry by Forge College. I'm your chief engineer for today. We are taking all those theoretical concepts from our last explainer on runtime conflict detection, and, well, we're finally putting our hard hats on. Today's topic is applying Parallel Patterns Project Increment. We are going to build a fully operational parallel execution assembly line for Solana's sea-level environment. We're moving from abstract ideas into a concrete project increment, and honestly, it's going to be incredibly satisfying to see it all click together. Assuming we don't accidentally break the factory in the process.
Here's the blueprint for today's project increment. We're hitting 1. The integration challenge. 2. Batching transactions. 3. The validation checklist. 4. Deterministic retries. 5. Reproducible simulation. And 6. Submitting your artifact. Let's get right into it.
Section 1. The Integration Challenge, Connecting the Factory. So to start, we really need to bridge the gap between theoretical scheduling heuristics and a concrete, testable implementation. And you're probably wondering what every engineer wonders at first. How on earth do the scheduler's batch proposals actually get verified by the runtime without everything devolving into absolute chaos, right? I mean, if multiple transactions are trying to read and write to the exact same accounts at the exact same time, how does the system maintain order and prevent total state divergence? Well, the core dynamic here is actually beautifully simple. Scheduling proposes, and the runtime verifies. Think of it like a factory floor. The scheduler is this highly efficient conveyor belt, just pumping out proposed batches. But the runtime? The runtime is your strict, uncompromising, quality assurance scanner, verifying every single piece that comes down the line. The scheduler is all about speed and parallelism, sure, but the runtime is there to enforce absolute safety. Moving on to Section 2, Batching Transactions, Preparing Raw Materials. Now, before we can test that strict QA scanner, we need to feed our assembly line the right raw materials. For this project, you're going to need a minimum corpus of exactly 12 transactions. Why 12? Because we need enough volume to repeatedly hammer a few specific accounts to intentionally force conflicts. We aren't building this factory to handle easy, perfect conditions. We want to stress test it. We want to see how it handles a real traffic jam. And this transaction stream absolutely must be representative of real-world Web3 traffic, so you need a healthy mix. Include pure read-only transactions, isolated writes, and most crucially, conflicting sequences. Situations where one transaction is trying to write to an account while another is trying to read from that exact same account on the chain simultaneously.
This brings us to batch metadata, which is an absolute game changer here. For our QA scanner to actually work, the scheduler has to attach accurate batch metadata to every single proposal. That means passing along the transaction IDs and explicit lists of which accounts are being read from or written to. Because if the runtime doesn't have a clear map of what accounts a transaction intends to touch, it's flying completely blind. It literally cannot keep the execution safe.
All right, Section 3, the validation checklist, quality assurance.
So the batches are formed, they've got their metadata, and now they hit the validation pipeline. These act as 3 sequential security filters that progressively narrow things down. Step 1 is the static overlap check. This is a quick guardrail catching obvious static hazards just by looking at those declared read and write sets. Step 2 is the speculative version recheck, which defends against stale assumptions by making sure account versions haven't shifted since the batch was proposed. And finally, Step 3 is post-speculative validation. This is what catches those sneaky, race-induced mismatches that manage to slip past the first 2 cracks.
Next up, Section 4, Deterministic Retries, Handling the Rework Pile.
Okay, so what happens when a transaction inevitably fails one of those filters? Well, it gets bumped to the rework pile. And let me tell you, non-deterministic retries, that's basically like toddlers fighting over a toy without adult supervision. It is an absolute guarantee of chaos and permanent state divergence. No way. You must establish a deterministic retry rule. You need a strict, entirely predictable rule for handling aborted transactions so that no matter how many times you run the simulation, you get the exact same reproducible outcome. There's actually a fascinating contrast in strategies here. You've got a conservative policy, which retries transactions in their original order. It's a bit slower, sure, but it is highly reproducible. On the flip side, an aggressive policy chases massive throughput but demands intensely complex recovery logic. For this explainer artifact, we're going conservative. I want you to retry the transaction in the next batch using its original input order. And if it aborts twice, escalate it to a serial execution slot so it runs in complete isolation. You'll see this trade-off between throughput and safety everywhere as you dive deeper into Web3.
Section 5. Reproducible simulation. Testing the line.
With the theoretical machinery built, we finally get to turn the power on. We have to run end-to-end simulations to prove our factory produces bitwise identical final states. Your simulation harness is going to loop through these exact steps repeatedly. You'll load your transaction stream, ask the scheduler to form batches, run the runtime validator, carefully reassign any deterministic retries, and output your final snapshot and log. Just keep looping that until every single transaction either commits in parallel or resolves safely in a serial slot.
Now, when you test this, you're going to run your harness 3 times, and you might run into the dreaded question, why are my simulation hashes mismatching? Listen, if your final state hashes don't perfectly match across those 3 runs, it means you've got a non-determinism leak. Something unpredictable is sneaking into your assembly line. Hunting these leaks down is like trying to find a ghost in the machine. It is an engineer's worst nightmare for sure.
But here's the trick to fixing it. Output a normalized log. Variable data like wall clock timestamps or randomly generated execution IDs are obviously going to change every time you hit run. You have to write logic to strip those out entirely. For example, just set all your timestamps to 0. That way you can compare the actual execution logic bit for bit without all the noise of changing time.
Section 6. Submitting your artifact. The final inspection.
Once those final state hashes perfectly match across all your runs, it is time to package your artifact for submission. Use this cheat sheet table to make sure you include every required file in the exact right format to pass inspection. Annotated scheduler batches as a JSON array. Your normalized runtime log as plain text. Your final state snapshot, binary or JSON is fine. And, crucially, a beautifully written Markdown README explaining your design rationale.
And hey, on that README, please don't just give us high-level fluff. You must include 3 concrete log excerpts that explicitly explain why the runtime chose a specific resolution action. Prove to the reviewer that you know exactly why a transaction was passed, retried, or escalated to serial execution.
Because balancing these precise trade-offs, knowing that conservative policies reduce parallelism but increase reproducibility, while aggressive policies increase throughput but demand stronger validation, that right there is the hallmark of a great Web3 engineer. This artifact proves your integrated understanding of how scheduling and runtime environments communicate. You're not just writing code anymore, you are choreographing a complex system of traffic control.
As we wrap up, I want you to leave with this final thought. Look closely at your logs. Which accounts experienced high contention and where did serial escalation actually occur? Really think critically about where your system bottlenecked. Why? Because in our next lesson on resource management in C-level, we are going to take those exact access patterns and use them to intelligently budget, compute, and account locks. It's going to be awesome. To explore more of these concepts and level up your skills, definitely visit forge.college. Keep building, and I will catch you in the next explainer.